Hey, welcome back. It's podcast 6.3, Quantum Mechanical Model. We're still in our Unit 6 about atoms, and boy, it's going to get fun now, so hold on. The quantum mechanical model is the most current understanding of what an atom looks like, but it was, at the time, a totally new approach. So there were three scientists actually involved in this process. We had Werner Heisenberg, and Erwin Schroedinger, and then this fellow named Louis de Broglie. And between the three of them, they helped to develop this entirely new approach to describing what an atom looks like. So de Broglie was the one who said that matter could be like a wave, just as we talked about in podcast 1. That matter could be like standing waves, which are more like the vibrations of a stringed instrument than ocean waves. So let's have a look at what waves look like. Here would be an example of a traveling wave where the energy is propagated across the medium as the wave travels. Standing waves still propagate the energy, but they result in no net movement of the particles. It's simply an oscillation of the particles, like we said, like the stringed instrument. So we see this waving up and down, but the particles don't actually go anywhere. They just oscillate back and forth. So an electron is much more like a standing wave than it would be considered to be like a traveling wave. So I'm hoping that by now you've seen the waves on a string simulation so that you can answer this question: what are the factors that would influence wave properties? We're certainly going to be spending time in class talking about those factors that influence wave properties and how much energy can be transmitted here. What I'd like you to do for this particular wave, for this standing wave that I have in the picture, I want you to identify the nodes and the antinodes, and I've labeled them A and B. Which one is which? In this picture, of course, the node would be the place where all the waves cancel. So here it's labeled B. That would be considered a node. Right here where there's no volume to it. And then for part A, the part that's labeled A, this is considered the antinode. So keep that in mind as we talk about what electrons look like and where electrons are around atoms. We're going to be considering electrons as waves in addition to electrons as particles, because it's both at the same time. So to understand where they are, we have to understand that they behave like a wave that has nodes and antinodes. So what is possible for our electron? Where is it allowed to be? The nodes and the antinodes describe where it's allowed and where it's not allowed. In fact, if you'll remember, node is like where it is node allowed. It's not allowed to be in the node. Node allowed. So in the atom, there are certain allowed waves, and these allowed waves are called electrons. Waves called electrons, you betcha, because electrons get to be waves and they get to be particles. So it was in 1925 that Schroedinger described the wave function of the electron. The wave function, in other words, some function f of x that could describe where the electron is. It's complex mathematics, but the most important part are the solutions to the math. So let's have a look at this. The wave function is described as a three-dimensional function. So we use x, y, and z, for instance, to describe where the electron is. And the solutions to these equations are called orbitals. So we talk about the different kinds of orbitals that would be allowed, represent the different antinodes where the electron's allowed to be. Each solution then is tied to a certain amount of energy. Heisenberg, though, said that in his uncertainty principle that there is a limit to what we can truly know about the electron. We can't know how the electron is moving or how it gets from one energy level to another. There's a limit of how well we can know the position of the electron and the momentum of the object. Because, you see, to spot an electron, we have to shine a light on it. And as soon as we shine a light on it, then it's not where it was when we saw it. So, it's complicated, this whole uncertainty business. But here's the equation that describes uncertainty. Heisenberg's equation says that the uncertainty in x, or its position, multiplied by the uncertainty in its momentum, is going to be some minimum value that's always the same. And it's always going to be equal to Planck's constant over 4 pi. You see, this is why Planck got to have a number named after him, because it kept coming up. That same number kept coming up time and time again in quantum mechanical equations. So we get to name the number after him. Like 3.14 keeps coming up in geometry, and so we name the number after pi. Well, Planck's constant gets to have its own letter h. So the delta x, again, describes the uncertainty in the position. And then the delta mv is the uncertainty in momentum. And since lowercase p is used for momentum, you may see it written like this in a book or on a website, that delta x times delta p is equal to 4 pi, equal to h over 4 pi. That's the uncertainty principle that describes how well you can know one or the other. So the minimum uncertainty that there will be in any measurement is going to be equal to Planck's constant divided by 4 pi. Let's look at an example of this. So we want to describe the uncertainty in the position of an electron that has a mass equal to 9.31 times 10 to the minus 31 kilograms, and an uncertainty in the speed, so its speed uncertainty is going to be 0.100 meters per second. So the uncertainty in the position, delta x, is going to be equal to h over 4 pi divided by the uncertainty in its momentum. So the mass times the velocity. So we're going to use Planck's constant again. What was that? 34, right? Joules times seconds divided by 4 times pi. And just use the button in your calculator that says pi, times the mass, 9.31 times 10 to the negative 31 kilograms, and multiply that by the speed, 0.100 meters per second. So what would that uncertainty be? Let me get my calculator out and you get your calculator out. It's not moving very fast, is it? So 6.626 raised to the negative 34 power divided by the product of all this mass. So our uncertainty in the position is 5.66 times 10 to the minus 4 meters. So in terms of the electron and where we want to locate it, say you're looking at an atom, and the distance between two atoms is measured in angstroms, which is nanometers to picometers, so very tiny distances. And this 10 to the minus 4 is like, this would be 566 micrometers. So that is almost 1,000,000 times bigger than the distance between two atoms. So you're only off by, a million times if you're guessing where it is. That's a pretty significant chunk to be wrong by. So uncertainty means we don't really know where the electron is right when we're trying to look at it. We can see where it was and where it's headed, but not where it is. Or we might know where it is, but then it's like frozen in time and we don't know really how fast it's going. Let's look at another example. What is the uncertainty in the position of a baseball? Well, what do you think? Do you know where a baseball is? Let's see. So delta x is equal to Planck's constant, 626. I always forget that extra 6 in there, times 10 to the minus 34 joules times seconds. And then we're going to divide by 4 pi times the mass. So for our baseball, it's 0.145 kilograms. And multiply that by the same speed that our electron had. So, just to have a fair comparison, we'll just keep that speed the same. And that's a pretty slow speed. Actually, that's the uncertainty in the speed. That's not the actual speed that it's going. I don't want to mislead you here. Okay, so the amount of uncertainty, the amount that I might be off by when I'm estimating the position of my baseball is 3.64 times 10 to the minus 33 meters. So in this, I was off by a factor of 10 to the minus 4 meters, which is in micrometers. And for this one, I don't even have a prefix for 10 to the minus 33. How come I didn't get all my 3's? 33. 10 to the minus 33 meters. Wow. So I can know the position of a baseball with much more precision than I could know the position of my electron, simply because the baseball is, wow, can't write and talk at the same time. I can know the position of my baseball with much more precision than I could possibly know the position of my electron, simply because the baseball is much more massive than my electron. That's how Heisenberg's principle applies to what we know about electrons and atoms. So the wave function basically tells us this. The square of the wave function will give us the probability of finding an electron near a particular spot. Probability. And the best way for us to visualize a probability would be to map out the places where the electron is likely to be found. So you might notice in the background of my slide I have graphs that kind of look like topographic maps. Well, these really are the graphs of the positions of atoms, and graphing them helps us understand where they are. So the probability of finding an electron decreases the farther from the nucleus that you go. So as you go farther away, the chance of finding an electron there declines dramatically, right? The farther we get away, the less tightly it's going to be held, so we won't find it there very often. And if we take the sum of all of the probabilities for all of the antinodes, all of the allowed positions, then we get a graph that looks something like this, where this peak here, this little bump, describes like the most likely place to find an electron. So for different energy levels, we would get different locations that are more likely than others. Let's have a look at that. If we can define the size and the shape of this graph, then what we're doing is defining the nodal surface. Where are the nodes? Where is it not allowed to be? And then we would define the antinode by defining the size that encloses 90% of our total electron probability. So we're not really describing a certain distance away from the nucleus, but rather a most likely distance. So for the first solution of Schrodinger's equation, the shape of the graph is a sphere for energy level 1. That's why we get the 1s orbital. So here's an example of those s orbitals where you can see in the first energy level we have a place where the electron's not allowed to be. That's the nucleus. The electron's not allowed to be in the nucleus. And then outside of here, it's not allowed to be anywhere outside of here either. So that's one of the nodes. But within this sort of pinkish hue, then we have 90% probability of finding the electron within that shaded space. So the 1s orbital is a spherical shape. Now in the 2s we have this piece, then we have a node, then we have this other piece. So the node is where it's not allowed, but we have two antinodes where the electron is allowed. Same in the 3s, only in the 3s we have two nodes and we have three antinodes for the 3s shape. So that's how the nodes and the antinodes in an s orbital would work, and for basically all of the orbitals we're looking at, we would compare the node to the antinode. Where is it allowed? Where is the electron not allowed? So we define all of these shapes by quantum numbers. There are many solutions. We looked at the first solution that has the spherical shape, but there are many solutions to Schrodinger's equation, and each solution can be described with 4 quantum numbers. And each of the quantum numbers will describe some aspect of the solution. We'll start with what's called the principal quantum number, n, that describes the size and energy of the orbital. You've used this before when we were doing Bohr models. N was our energy level, right? Well, now we're going to add a little bit more detail, as we always do in AP Chemistry, to what you learned about atoms before. So n is called our principal quantum number, and it has integer values, whole number values, that are always greater than 0. So n is the principal quantum number. That describes our energy level. L is a little bit strange. It's called the azimuthal quantum number. And this describes the angular momentum, but we call it the shape. So the azimuthal quantum number corresponds to the shape of the orbital that the electron will be found in. The m sub L is what we call the magnetic quantum number. We can define whether or not something is magnetic, diamagnetic, or paramagnetic according to what we get for this magnetic quantum number m sub L. It always will have integer values between negative L and positive L. So whatever number we have for the azimuthal is going to determine what's allowed for m sub L. And then m sub S is called the spin projection. Remember, electrons can spin up or they can spin down? Well, that's just the way we draw the arrows. They have a spin number of positive half or negative half. So by up and down, we don't really mean just up and down in space. It could also be spinning around in a circle this direction, right? And we would still consider that opposite of the one that's spinning this way, because, you know, they spin opposite directions. That's all we need. So let's look more closely at the shape of our orbitals. The L, angular momentum, defines this shape. And notice that I've written these all in sort of a cursive script so that we don't get confused with n as the number of moles or confusing the L as the number 1. But L defines the shape of our orbital, and when L is equal to 0, we call that the S shape. The S orbital is a spherical shape. When L is equal to 1, we call this the p orbital that has sort of a petal shape. The d orbital is when we get an L equal to 2. And now I'm done drawing orbitals because I don't draw well in 3 dimensions on a 2-dimensional surface. And then the L that's equal to 3 is called the F-shaped orbital. We could have something more than F, and electrons do actually go into higher orbitals than the F shape. It's just that they aren't naturally found there in their ground state. We have to add energy to get them to go into other ones. So we're going to summarize what we know about the quantum numbers, just to make your life easier so you can keep these straight. Remember, N is our shell, or the energy level, where we would find the electron. And the range of values for N is anything greater than 0. Oops, got to write it in cursive. N greater than 0, so we could have 1, 2, 3, and so on. Oops, I meant to write that over here. So N has to be equal to anything greater than 0, some positive integer value. And the azimuthal quantum number has the symbol L, and it's defining our subshell. So within that shell, we want to know what shape it has, like S, P, D, or F. The range of values for L is pretty straightforward. L can be anything from 0 all the way up to n minus 1. So whatever n is here defines how big the L can be. So for instance, if we had energy level 3, then L can have values of 0, 1, or 2, but nothing higher than that because we can only go up to n minus 1. Now the magnetic quantum number has the symbol m sub L. This describes the energy shift for our electron, and it can have values that range from negative L up to positive L. So the value that we have for the orbital in L describes what we get for the magnetic quantum number. So for an L that's equal to 2, what could we possibly have for m sub L? We could have negative 2, negative 1, 0, positive 1, and positive 2. So from negative L up to positive L, and anything in between, we can have those values of m sub L. So where L is equal to 2, which is our D shape, we have 5 different magnetic quantum numbers. 1, 2, 3, 4, 5 different magnetic quantum numbers into which we can fit exactly 2 electrons for a total of 10 electrons held by a D orbital. Now let's look at the spin projection quantum number. This we call m sub s. And this describes the spin of our electron, up or down, right? So our values that we could possibly have is either negative 1/2, or we could have positive 1/2 for an electron. That's it. So it's either negative 1/2 or it's positive 1/2. And that's all that there can be for our spin projection quantum number. So we're going to be applying these to situations where you already know how to locate electrons in Bohr diagrams and Aufbau diagrams. We're going to apply quantum numbers to what you know. So where we have s orbitals, we can have these in any energy level that's greater than 0. So 1 and all the way up to whatever we need, right? Our periodic table goes up to energy level 7. We could possibly go higher because we can add more energy than that, but there would be a certain limit. You add any energy that's too much and you're going to remove the electron entirely. Then our L value for the s orbital is always 0 because 0 describes the shape of s. So if our L is 0, then what could m sub L be? It's either negative L or positive L. And since L is 0, the only thing we could have for m sub L is 0. And then for m sub s, we can have 1/2 positive, or we can have 1/2 that's negative. That's why there can only fit 2 electrons in an energy level that's described as an S shape. So the s orbital holds 2 electrons, and that's it, because m sub L is 0. Now let's look at p orbitals. P orbitals don't ever even start until we get to the second energy level. So in the second energy level, let's look at the 2p. Where n is equal to 2, what are the possible values for L? L can be either 0 or it can be 1, where 0 describes the 2s orbital that the first 2 electrons go into, and then the L equal to 1 describes the p orbital, the 2p, into which the next 6 electrons can fit. And here's how. Where L is 1, m sub L can be -1, 0, or +1. And into each of those, my m sub s can be +1/2, or it can be -1/2. So we get to put 2 electrons in each of these spots. And that's why we have 3 different shapes of p orbitals, the px, py, and pz, because of the magnetic spin number. And then the spin projection gives us our electrons going up and down in each of these for a total of 6 electrons that will fit in p orbitals. All right, we catching on? So here's all 3 p orbitals graphed together on the same quadrant, so you can see how they line up. They don't interfere with one another because they each line up along a different axis. In the d orbitals, though, they don't line up along the axes, but rather within the quadrants, quadrant 1, 2, and 3, in the planes of dx, not dx, the xy, or the zy, or the xz, or the yz. And then, of course, we have the donut orbital, and that's the one that helps me remember that D stands for donut. What's the shape of a d orbital? It's pretty complex, but there's one that has a donut around the middle. All right, so the L equal to 2 is the one that defines the d orbital. And since we have 5 shapes, that means it can hold up to 10 electrons. Then finally, in the quantum mechanical model, we have this f orbital. So for the naturally occurring elements, we only go up to f orbitals where L is going to be equal to 3, and then if L is equal to 3, then m sub L could have all of these values: -3, -2, -1, 0, +1, +2, or +3. And so how many different shapes is that? That's 1, 2, 3, 4, 5, 6, 7 different places where electrons can go, either spinning up or spinning down. 7 different places. Here's a picture of 3 of them, and then the next 4 look like this. So that's what f orbitals kind of look like when we graph them in a 3-dimensional coordinate system. That's the quantum mechanical model. So we're going to be using these quantum numbers to describe where the electron is. We're locating the electron like we'd locate your house. We use its address, and we find where it is, and that's it. So I'll see you guys in class tomorrow.